All right, so today we are covering Chapter 4 in the textbook. All right. And so in Chapter 4 we are exploring relationships. We are exploring relationships between numeric variables. Okay? So what we are doing is we are looking at two numeric variables at the same time, and we want to see if there is a possible relationship between these two numbers. Okay? So the book starts off and it says, we're going to look at the 50 states plus DC. Okay, so this is example 1. We have 50 states plus DC. Okay, so these are our observational units. We have 51 observational units. So if we're thinking of our raw data table, we're going to have pretty much at least 3 columns in it. Okay, and this is the columns are the state, and then we're looking at 2 numeric variables, which is median age of marriage for men sorry, it's like squished in there. And then the second variable that we're looking at is median age of marriage women. Okay, so these are not individual marriages. This is just like if we list off the states, we have Alabama, Alaska, Arizona, etc., right? Okay, and then what these numbers are, they are they're looking at just looking across all of the marriages that have been filed in Alabama. Okay, so you've got lots of marriages, and then they're just asking what is the median age of marriage for the men in Alabama. Okay, so maybe it's like for what is it? I don't know. So let's say 100,000 people got married that year or something. Okay. And then you just say out of those 100,000 couples, and this is assuming male and female couples. I know that's not always the case, but for this data, it's male and female couples, and we're looking at for Alabama, what is the median age of marriage in Alabama? And so maybe I'm just making up numbers. I have no idea. Okay, so maybe it was 24 years old for women and 26 years old for men or something. Okay, I don't know. All right, and then and so these are not individual marriages. These are just across the board. What's the median age of marriage in Alabama and the median age of marriage in Alabama for men and women? Okay, and then maybe in Alaska, it's like the median age of marriage for women is 28, and the median age of marriage for men is 30.5 or something like that. Okay, we're just making up numbers here. Okay, and so we've gathered data here for every single entry, and what we're going to do is we're going to take one of these columns and we're going to just call it X, and then the other column we'll call Y. Okay, and these are arbitrary, but this is how we'll do it. Okay, and then we're going to graph these. Okay, and so we'll start down here, and we'll go 23, 24, 25, 26, 27, 28, 29, and 30. And over here, I guess it starts around 25. Okay, and so we create. We're going to create we're going to plot each of these rows as coordinate pairs. All right. So when I plot Alabama, I'm going to be at 24 for X. Okay. Median age of marriage, women 24 for X, and 26 for Y. So Alabama will get a dot right there. Okay, and again, I'm making these numbers up. And Alaska, 28 and 30.5. So they'll get a dot somewhere like right there. Okay? And who knows, if we went to Arizona, maybe it's 26.5 and 29. Okay, I don't know. All right, so 26.5 and 29. Shows up right there, okay? So, these are just 3 data points, okay? If I plot every single one of these, how many dots will show up in my scatter plot? 51 dots, right? So this is if I plot all the dots, or if I plot all rows, I will have 51 dots in my scatter plot, okay? And so, yes, this type of diagram is called a scatter plot. I guess that's one word. And you're pretty much treating these as coordinate pairs. So just like, when you took algebra, you plotted your X and Y, we're going to plot these. Okay, so, these 3 dots that I've graphed in the beginning will show up, and I'm just going to pretend to put, 50, 40, whatever, 8 more dots, so that we have a total of 51 dots, and then we get a plot that looks something like this. Okay, and this is figure 4.1 in your textbook. So when you go through and do reading in the textbook, this is supposed to be like figure 4.1 in the text, okay? And so what we do, or what we say when we look at a scatter plot like this, or we ask, is there a relationship between the median age of marriage for women and the median age of marriage for men? Okay, is there a relationship between these numbers across our 50 states plus DC? Yes, okay, and what would you say that relationship, how would you characterize that relationship? So just, at the loosest relationship, we can basically say, in general, if the age of marriage for women is high for the state, the age of marriage for men is high in the state. And in general, if the age of marriage for women is low in the state, the age of marriage for men is low in the state, and vice versa, okay? So, we can just kind of make a statement. So, general statement to describe the relationship. we'll say, you know, in general, if the median age of marriage for women is high in the state, the median age of marriage for men is also high, okay? And then, you know, we can kind of pretty much say the exact same statement, dot, 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 dot. If it's for, you know, age for women is low, then age for men is also low. Okay, something like that. Okay. So far, so good? Okay. And we can further, you know, we can try to draw a, you know, a straightish line through this, something like this, okay, to kind of say something like this is our trend line. And if we had to describe the trend line, we could say something like, you know, so the trend line goes even further, and rather than just saying things like, if the age is high for women, it's high for men, we might go ahead and try to quantify something like this. And I think I heard a student say something along these lines, which is, you know, the median age of marriage for men is about 2 years older than the median age of marriage for women in general. Okay, if we're looking across the states, it's something about 2 years, and probably not exactly that, but we can say something like that. Okay, so, you know, so if, you know, if I'm telling you a couple is getting married and the woman's age is 28, your best guess for the man's age would then be something around 30. Okay, if you know nothing else about it. Okay, so so maybe for the trend line we can go a step further and say something like median age of marriage for men is about 2 years more than, I'm going to just call it age for women. Okay, and so this is kind of where we are headed in this chapter. All right, so we'll talk about scatter plots in, you know, a little bit more detail, and just talking about identifying key components in a relationship between two numeric variables, and then we'll talk about determining the trend line and how to interpret the trend line and things like that. Okay, and so again, you know, one key thing that we cannot forget is that this chapter only applies for relationships between two numeric variables. If you don't have two numeric variables, this is not going to work. So if one of them is categorical, it's not going to work. Okay, and so, you know, we think about men and women, and that's a categorical variable, but we are not dealing with categorical variables here. We are dealing with a numeric variable, which is the median age for men, and another numeric variable, which is the median age for women. Okay. All right. May I flip to the next slide here? Looks like we're good. All right. Okay, so we can talk about the trend, and we'll say describing relationships. So trend is often also called the direction of a relationship. Okay, and so we have positive association. Okay, and we also have negative association. Okay, and what positive association is, positive association means as one variable increases, the other variable also tends to increase. Okay, so okay, or succinctly, we can just say large X is associated with large Y. Okay, and small x is associated with small y. Okay, so that's a positive relationship. These two things go together. And a negative relationship or negative association is just the flip of that. Okay, so as one variable increases, the other variable tends to decrease. Okay, so we can kind of summarize this with saying large X is associated with small y, and small x is associated with large y. Okay, in general. All right, so what this looks like is positive association looks, if we create a scatter plot, positive association looks something like this. Okay. So remember, as we go to the right, this small x is over here, and large x is over here, and large y is up here, and small y is down here. So small x is associated with small y, large x is associated with large y. That's what we have in this graph. Okay, and so the book's example is, we could say x is the age of a vehicle, okay, and then y is the mileage on the vehicle. Okay, and so, you might find a 10-year-old car that doesn't have very many miles on it, but in general, cars that are 10 years old, we're going to have more miles on it than cars that are 2 years old, okay? And so in general, large X, old cars, associated with large Y, lots of mileage. Small x, a newer car, associated with small y, less mileage. Negative association looks just the opposite. So each dot is a different observational unit, whatever that might be. Okay. Okay, and so this is negative association. Okay, so again, large X is on the right, small x is down here, so we have small x and large X. And this is, small y is always at the bottom, and large Y. Okay, and so one example that the book provides is, looking across different countries, okay? If we look at the literacy rate of a country, so this is countries that have high literacy, meaning everybody is able to read, and over here we have countries that have low literacy. Looking across different literacy rates, we can look at the Y. This is births per woman. Okay, so what this means, okay, so down in this region, these are countries with high literacy. And what we see is that, in general, the women do not have as many children, okay? Fewer children per woman, okay? And over here, these are countries with low literacy, and then many births per woman, okay? And so that is the description of trend here, okay? This brings up a good point that I will address later, is that association does not mean causation, okay? So just because you see a relationship between two variables doesn't mean that one thing is causing the other, okay? So we cannot say that if a woman learns how to read, that means she's going to want fewer children, okay? That it doesn't work that way, all right? There are lots of factors going into literacy rate for a country, lots of factors. There's lots of factors that go into how many births per woman happens in a country, okay? Lots of different things, from culture to religion and all sorts of things, even just access to education and all of this. This is all sorts of things, so we cannot say that just because as X goes up and Y goes down or goes up, one thing causes the other, okay? We can't even say, just from looking at a graph, we can't say that as a car gets older, that means there's going to be more mileage on it, okay? Because we know a car can sit in a garage and get older, but not gain any mileage. But in general, we see these things working together. So we cannot say one causes the other, right? So I'll write that down a little bit more formally. But here we're just talking about positive and negative relationships. Okay. We can talk about the strength of a relationship. Oh wait, actually, before we get to strength of a relationship, sorry. Let me just also we have we can say not positive nor negative as far as trend goes, okay? And there are definitely different ways that not positive nor negative can look, okay? So we have just kind of like a scatter, a cloud of points, kind of like this. And so what this means is that x and y are not strongly related to each other, okay? So that this is, you know, no real trend or relationship between x and y, okay? So we have, you know, large values of x, so, you know, over here this is our high x, and this is small x. So high x can be associated with large values of y and small values of y. Over here, smaller values of x can be associated with larger values of y or smaller values of y, okay? Okay, so large x can go with large y or small y, and vice versa, okay? Small x can go with large y or small y also. So this is no real trend, okay? Other times you get examples, and so, you know, the book shows kind of, you know, these curved relationships. Something like this, okay? So here there's clearly some kind of relationship between x and y. Okay, so there's, you know, definitely a relationship exists between x and y. Okay, so, but a single word like positive or negative is not going to be able to describe this entire the whole relationship, okay? Yeah, I mean, probably, you know, we could even kind of split it into three zones right here. You know, for x over here, it's positive. For x over here, there's not, you know, maybe a weak relationship, and down here, it's definitely negative. So there's definitely some kind of relationship between x and y, but a single word, positive or negative, will not be sufficient. Okay, so these types of relationships also exist. This could be, you know, we throw a ball in the sky, and so x is the time, you know, and so in the beginning, you know, or like the time since I've let go of the ball, right? So in the beginning, when I let go of the ball, it's close to the ground and it keeps going up, 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 and then y could be the height, but then as time goes on, it starts falling back down, or something like that, okay? We'll say altitude. So, so definitely there's some kind of relationship that exists between x and y, but positive or negative is not enough to say that. So, and then sometimes you just kind of have this relationship, or like a non-existent relationship. You just have this cloud of points where knowing something about x really doesn't give us much information about y. This could be something like your shoe size and your IQ score, or something like that, right? So we can have people with big shoes, big shoes that can have high IQs and low IQs. We can have people with small shoes with high IQs or low IQs. Okay, so shoe size for x, and then y will be IQ. I use IQ as an example a lot, but I don't know if people actually get their IQs still tested or anything like that. But I think we kind of get the general notion of IQ relating to, I don't know, somehow being related to intelligence, okay? All right, so we also have strength of a relationship. Okay, and so with the strength of a relationship, we use terms like weaker association, weak association, okay, or strong association. Okay, and so weak association, this is kind of the idea of, more scatter in our plot. Knowing X, gives us a little bit of information about Y, but, our predictions of Y based on X are less likely to be accurate. This is another way we can think of it. Okay, strong association, you're going to have less scatter in the plot, and predictions of Y based on X could be very accurate. Okay, and so I'm going to kind of exaggerate this concept of we're going to have two relationships. Both will have positive trend. Okay, so positive association. Okay, but weak association. And over here, we will also have positive association and strong association. Okay, and so positive and strong will look something like this. Just have a little bit of scatter. So this would be, really, really strong. Okay, and then weak association, you'll still kind of have this overall positive relationship, but definitely there's more scatter in your plot, something like this. Okay. So in both cases, there's definitely a positive relationship. But over here, this would be a weaker. So this could something. So the examples that the book uses is using your height to try to predict someone's weight. Okay. So in general, taller people weigh more than shorter people. Okay, but you can have short people with high weight. You can have short people with low weight. You can have tall people with high weight, tall people with low weight. Okay. My graphs are very much exaggerated versus maybe what the actual data shows. Okay. Over here, on the other hand, this would be waist size and weight. Okay, so if you wanted to predict someone's weight, their waist size is generally a much better way to predict. Okay, so if someone has a small waist, in general, their weight will be quite low. All right, and if someone has a very large waist, their weight will be quite high. And yes, you will have some variation, and the real data is going to be a little, more scattered than what this plot shows, but the association between waist size and weight is stronger than it is between height and weight. Okay. Okay, so that's describing the strength of a relationship, and then lastly we have the shape of a relationship. Okay, and the shape of a relationship As far as this class goes, we're going to have linear, which basically means straight line, or resembling a straight line, I should say. Okay, and we have nonlinear. So everything else, if it doesn't resemble a straight line, we're going to say nonlinear. Okay, and the truth is we can be much more specific about things being nonlinear. You can take an entire course devoted to this topic of regression and relationships between variables, and you'll have other words like exponential and quadratic and polynomial and all of these different things to describe a nonlinear relationship. But as far as this class goes, we're going to just have a straight line relationship or anything else. So if it looks like that, it's not a straight line, okay? Or if it looks like this, it's not a straight line. Okay, and so if the data, even if there's a scatter and stuff, if overall it looks like a straight line kind of does the job, then linear, we're happy with it. Okay, nonlinear, if it seems like a straight line is not going to do the job, then you've got this. Okay, other examples of you can have data that looks like that creates a funnel or something like this. Okay, this is also going to be an issue. All right, so anything, if a nice straight line doesn't work, then we're going to just say nonlinear. Okay, and as far as our class goes, we're only going to consider linear relationships. Okay, so we will only I guess do analysis for linear relationships. Okay, and so if you see something that doesn't fit a linear relationship, you can just say this is a nonlinear relationship, and it will not work. Okay. One thing that we also have to be mindful of is the existence of outliers in our data, okay? Because they can definitely throw things off, okay? So just be mindful. Of outliers. Okay, so outliers, we're just going to kind of take a loose definition. So we've already learned kind of one way to identify outliers with like a box plot. If it shows up as circles, then those are considered outliers. In here, it's just if certain dots don't fit the overall trend, we might consider these outliers. Okay, so these are data points that deviate greatly from the overall trend. Okay, so an outlier could look something like we have, this is kind of our data points over here, and then you have something way over here. This would be an outlier, okay? And if you tried to do your analysis with this outlier in it, it will definitely throw things off. And so you should investigate, what is this? What is this data point, okay? And if it's, sometimes it can be explained as, with a typo, all right? Maybe the person who entered the data maybe this dot actually belongs over here, but whoever typed it in entered one of the numbers wrong, and so it ends up over here, okay? So sometimes outliers exist because of typos. Okay, and in that case, remove the outlier. Okay. Other times, the outlier is truly just an unusual point, okay? Okay, and in these cases, you should do two analyses. One analysis where you include the outlier, and one analysis where you get rid of the outlier, okay? Okay. All right, so again, just to kind of recap. So when describing a relationship, between two numeric variables, okay, you should look at mention, well, I'll start off with shape, okay, but then also the trend or direction, whether it's positive or negative, and the strength. Okay. So shape, linear or nonlinear. Direction, positive, negative, or neither. Strong or weak. Okay. All right, and so we have a numeric summary that captures this information, okay? See, we've already learned several numeric summaries, and your quiz covered a lot of these, such as the mean and the median, which describes where the center of data lies, or the standard deviation, or IQR, which describes the spread in data, okay? And if your data consists of two numeric variables, we also have a numeric summary that describes the trend and strength, okay, or direction and strength of a relationship. Okay, so that we have a numeric summary. Describes the trend or direction and strength between two numeric variables. Okay, so this numeric summary is called correlation. Correlation. Sometimes the full name, I'll guess, is called the correlation coefficient. often just called correlation. Okay, and the symbol is R. Okay, so the correlation coefficient, or R, is just it summarizes the direction and strength. Okay, the correlation coefficient is it's just kind of the result. You throw in your data into a formula and it spits it out. Okay, the formula is rather complicated, so we're not going to bother with calculating the correlation coefficient in this in this class. Well, we're not going to bother. We'll do it by hand. And in general, we just kind of throw our data into a computer or a program, and we just say, hey, calculate the correlation for me, and the computer will do it. Okay. The important thing is understanding what correlation means and how to use it once you have the thing. Okay. So correlation can be calculated for any data set with two numeric variables. Okay. The calculation of correlation is rather tedious, so we will not cover it in class. Okay, so instead, okay, we ask computers to calculate correlation for us. Okay, and the important part is the interpretation of the correlation. Okay, all right, so here's one key, all right? For any of the interpretations of correlation to be true, the relationship must be linear, okay? You can calculate correlation even if the relationship is not linear. You can just throw your data into the formula and it will spit out a number. But if the relationship is not linear, the number that you get back is will not have, or the interpretations based on that number will not be correct. Okay, so you always, and the only way that we have right now to decide if a relationship is linear or not is to create a scatter plot and look at it with our own eyes. Okay, and our eyes and our brain is actually much better than well, I don't know, maybe computers are catching up, but much better than any other system or formula that we can set up for trying to decide, are these kind of in, are these in a straight line? Maybe, maybe not. Okay, that's, our eyes are very good at identifying patterns like that. Okay, so the important part is the interpretation of correlation. Okay, so what I just said is our interpretations of correlation will be accurate only if the relationship is linear. Okay, so always graph your data, always graph your data, look at it, and decide if it is linear or not. Okay? Because again, you can You can get the correlation even if it's not linear. It's just not going to have any meaning. Okay, so this is what we have. The sign of R, so whether it's positive or negative, is the direction or the trend. The sign of R, sorry. Direction of the relationship. Okay, so, you know, if R is positive, the direction is positive. Okay, negative R, negative direction. Simple enough. Okay, so R is always between -1 and 1, or +1 inclusive. Okay, or we can say -1 is less than or equal to R, which is less than or equal to 1. And so when R is close to 0, the relationship is weak. And when R is far from 0, meaning close to 1 or close to -1, the relationship is strong. Yes, question?
Is the sign there right? If it's at -1, greater or equal to R?
Is -1 is less than or equal to R, less than or equal to +1, right? So, I'm sorry, you were asking about this part?
Yeah, if they'll be like size are equal and then smaller or equal to the second.
No, I'm pretty sure I've written this correctly. So, yeah. So, yeah. Okay. Sorry. Yeah. I mean, if it's easier to understand it this way, R is always between -1 and +1. That's fine. Okay. You know, in math we often use symbols as kind of shorthand or shortcuts for writing things out, and so this would be the shortcut for writing it out. Okay. Okay, and so you know, so what this looks like is if you have something that looks like this. Okay, this is going to be R is equal to 1. Okay, that's like if it's perfectly straight line, you got no scatter. It's a perfect straight line. R equals 1, right? You can make perfect predictions of Y based on X, all right? So that's going to be R equal to 1. You got a little bit of scatter, something like this. This is probably R equal to like 0.92 or something like this. I'm just making numbers up, okay? You add a little bit more scatter. This is, I don't know, I'm just making stuff up, R equal to 0.7, okay? And so on and so forth until you get to the point where you have no relationship at all. the scatter gets bigger and bigger and bigger. So here you would have r equal to 0. Okay? And then, if you have a lot of scatter and but it's still overall kind of negative, this might be r equal to negative 0.3, I don't know, so on and so forth. The relationship gets stronger, less scatter, r equal to negative point, again, making up numbers here, until you get to -1. Okay, and so you can, this progression of different relationships, and they're, they list a whole bunch of these in the textbook on pages 149 and 150. Okay, so this, okay, yeah, there's actually quite a few interesting relationships that show up. Okay, and again, the key is correlation does not mean causation. Let's just look around and make sure I'm all caught up with the writing. Okay, so correlation So after I talk about correlation, we'll take a short break. But I probably got this slide, maybe one more slide. I don't know. Okay, but just okay. So correlation does not mean causation. Just because two things happen together, things seem to happen together, does not mean that one is caused by the other. Okay, so the example was literacy rate and births per women. Okay, we cannot say increasing literacy decreases childbirth. Okay. Who knows? Making the changes in the country that lead to increased literacy may also cause changes in birth rate, but the literacy in of itself is not the cause. Or, it could be the cause. We don't know, but just from looking at a graph, we cannot make these conclusions. Okay, so just have to be mindful of that. Okay. All right. So a few key points. Okay, a few key points about correlation. Okay, so the order of x and y does not matter. So the correlation between x and y is the same as the correlation between y and x. Okay, or we can if you want the math shortcut. You don't have to write it that way. Okay. Multiplying x or y by a constant or adding a constant will not affect the correlation either. Okay. Okay, so another way is to understand this is that changing the units. So changing units often involves adding a constant or multiplying by a constant. Okay, so changing units will not affect correlation. Okay, so maybe we did that. We took a bunch of measurements. We said, is there a correlation between someone's waist size and their weight? Okay, and we measured their waist size in inches, and we measured their weight in pounds. Okay, and we got a correlation of, let's say 0.85 or something like that. Okay, if we had chosen to use centimeters to measure waist size, or if we had chosen to use kilograms to measure weight, or anything like that, and so all of our numbers change because we're using different units, our correlation will still be exactly the same, okay? Because changing from centimeters or inches to centimeters or from pounds to kilograms just involves multiplying by a constant, okay? Or if you had to add a constant or something, changing from Celsius to Fahrenheit or whatever, which involves multiplication and addition and whatever, that will not change things, okay? So things like that, okay? Correlation R itself is unitless, okay? So when we look at the mean of a variable, it will carry the units of the variable. So if all of your variables were measured in inches or whatever, if you're looking at a bunch of people's heights measured in inches, the mean of these heights will be something inches, okay, which makes sense, okay? But correlation, there's no units. You calculate correlation between x and y, no units are going to be involved, all right? Okay, and again, correlation only makes sense. These interpretations, all of this stuff that I've written about correlation, this only works if the relationship is linear, okay? Again, just only works. So these interpretations about the strength and the direction and all of that, the interpretations for correlation only make sense if the relationship is linear. Okay, we'll take a 10-minute break here, and then we'll finish out the rest of chapter 4.